to the fourth in this semester's Heidelberg Joint Astronomical Colloquium, and this week we are very glad to welcome Noemi Globus of the University of California at Santa Cruz, who is an expert on many aspects of high-energy astrophysics, but is going to tell us again about the, as I'm sure will transpire, not unrelated topic of Chiral puzzle of life. And I call upon Noemi's host, Christian Fent, to make the formal introduction.
Yeah, hello, Noemi. Good morning. It's a very early hour in Santa Cruz, I suppose. It's my pleasure to introduce you to our colloquium speaker today. So Noemi arrived in Santa Cruz only recently. Before, she was a postdoc at Stanford University and at Flatiron Institute. She was also on a short-term 2-month trip actually to Tokyo in these times. And from 2012 to 2018, she was a postdoc in Israel at the Tel Aviv University and Hebrew University. And her PhD was from Paris, so from Observatoire de Meudon. It was 2011, and it was on the topic of relativistic jets and cosmic ray acceleration processes, which we will learn today is closely connected to this chiral puzzle of life. On a personal note, I have to say that it was exactly 10 years ago, November 23rd, that I left with a train to Paris to be her opponent for the thesis defense. This is when I met her first time. Yeah, so as Richard has told us, Noemi has a range of interest: high energy astrophysics, so jet formation, acceleration, and collimation of outflows, and the central engine of relativistic jets. It's particle physics, so it's the cosmic ray accelerators and the origin of highly energetic cosmic ray particles. And recently, and I'm not completely sure how she entered that field, it is astrobiology. So the chiral puzzle of life, that's the talk of today. And yeah, Noemi, please go ahead.
Thank you for the nice introduction. So, okay. So yes, I'm going to talk about astrobiology. So the title of the talk is The Chiral Puzzle of Life. And you see there are 3 pieces of the puzzle here. So on the left, you have a remnant of supernova. In the middle, you have a Feynman diagram showing a weak interaction. And on the right, you have a DNA molecule. So I will try to connect these 3 pieces during the talk. So that's the goal. And I will start with astrobiology, which connects astrophysics and biology. So this is the remnant, as I said, of supernova Cassiopeia A. And we know that supernovae produces heavy elements. So you can see them, they are outlined here in pink. And some of these elements are actually essential to humans, which are, we can be considered, I think, as a complex life form. But you can see that here they are outlined. Someone has his speaker still on. So I hear a noise. So there is outlined here in gray and light gray, the elements that are essential and suggested essential to humans. So as you see, it's, supernovae are very important for us. And you can see here also shock waves. The explosion energy is approximately the total solar radiated energy. We have one supernova occurring every 30 years per galaxy. And these shock fronts appear to accelerate cosmic rays. So the flux of cosmic rays is seen here on the right-hand side. And it's a power law. It's amazing how it's, I mean, straight over such a huge energy range. So the supernova are known to to be able to accelerate cosmic rays at maximum energy of around 100 TeV. We think now we have some sign of supernovae remnants that can accelerate even a bit more than that. So this is still an open question if regular supernovae can make it up to PeV. Then you have the knee of the cosmic ray spectrum, which is a feature which is known since the 50s. And in the community is known as the end of the light galactic component. And then starting somewhere at 10 to the 17 electron volts, where the Larmor radius start to be comparable of the size of the galactic disk, actually the cosmic rays are able to escape more efficiently from our galaxy. And somewhere here we have the transition from galactic to extragalactic cosmic rays. So around the knee energy, we have a flux of 1 particle per square meter per year. And below that, around TeV, it's 1 particle per square meter per second. So this cosmic ray, they will be trapped by the magnetic fields in the galactic disk, and we will be irradiated all the time by this cosmic rays. So not only supernovae provide heavy elements, but they also provide cosmic rays. And each time a cosmic ray will interact with the atom of our atmosphere, it will produce a shower of sometimes for the highest, very highest energy, over 100 billion of secondary particles. And so they will cascade. You have here a sketch which is taken from the Pierre Auger Observatory website, which is one observatory of cosmic rays. And at the ground level, so what are the shower components? You have another sketch here. So you have a proton that is initiated a shower of secondary, and basically you can divide the component of the cosmic ray shower into 3 different components. So electromagnetic, which will actually die at around 4. I mean, it will be really attenuated, something like around 4 kilometers above the surface. So actually, when you take a plane, this is what you will mostly get. And then at the ground level, we are going to be mostly dominated by the muon component. So yeah, I've made this to be really introductory, but if you have questions, because I don't really know the audience, please do not hesitate to interrupt me. So this is a sentence from my colleague Roger Blanford, who is actually working on this topic with me to make the connection between cosmic ray and the origin of life. So he says that cosmic rays like red wine are good for you. Why? Because at low flux, of course, they will induce mutations, and mutations are necessary for life. The mechanism, because as I said, at ground level, we are dominated by the muon component. And usually in laboratory experiments, when we study the mutation rate, we are using accelerators of electrons, or we are using X-ray or gamma rays. So we do not really understand how the muons actually interact to produce mutations. The mutation cross-section to muons have not been measured precisely. And also what we see now is, of course, lives that have evolved. So how do they produce mutation of early life form? This is also an open question. But as we know, heavy doses of cosmic ray are bad. We would have actually a problem if we would like to go to Mars, as you know. I will come back to this. And if we have a nearby supernova, that would enhance also the cosmic ray flux by several orders of magnitude. So this is another work we are doing with Anatoly Fedinich, who is also my colleague and now is in Taiwan. And you can see here you have a plot to show you the evolution of the radiation doses due to natural radioactivity, which is what is actually dominating now. And so these are the studies I took the evolution from. So this is the total cosmic ray, and you see that it's only around 10% of the radiation dose, not accounting for human-made radiation, of course. But if you have a nearby supernova occurring at something like 50 parsec away from us, then you see that this is basically because there are uncertainty in the model. So this is why it's going from something like 6 to over 100 milligram per year in radiation dose. But you see that it's anyway beating the natural radioactivity by orders of magnitude. So this would have certainly some effect. Okay, this is what I said. So the rate can be boosted for something like 10,000 of years. So that was for Earth. Of course, we can also study how these cosmic ray showers, these showers of secondary particles would develop at other environments that are prime target for the search of life in our solar system. So for a comparison, so you have here a shower induced by a 1 PeV proton, and you have the three components I was talking about: muon, electromagnetic, and hadronic, and the muons are in solid lines. So you see that on Earth, they are dominating at ground level. On Mars, the shower has no time to really develop because the atmosphere is so thin that the grammage traverse is very low. But for tides, these are worlds with very dense atmospheres. So you see that the muons are actually, the shower has time to fully develop something like around 50 kilometers above the surface. And this is actually interesting that the muons are dominated here also because for Venus, what they call the habitable zone is actually this layer of clouds which is around that altitude between 50 and 60 kilometers. So it's, I think, important to understand how muons actually interact with the molecule and if what role they play in astrochemistry and astrobiology. So now I will connect the supernova and the weak interaction diagram. So as you may know, the law of physics are not the same in the mirror because there is one force that actually can violate parity. So weak interact with neutrinos. Neutrinos are only left-handed. Antineutrinos are only right-handed. They are connected by CP transformation, and that was discovered in the late 50s. So it was shown that occur actually when you have natural radioactivity, and this tiny effect can lead to large consequences, as you know, baryon dominance. So why is it interesting here? What I introduce is that this actually has a consequence because the muons, the ones that are dominated on Earth at ground level, these muons come from a weak decay involving this interaction that is parity violating. So this means that this is what occurs mostly to produce muons in these cosmic ray showers. You have a decay of a positive pion that give you a neutrino and a positive muon, or a decay of a negative pion that give you an antineutrino and a negative muon. So this is in the pion rest frame. But because these neutrinos are chiral particles, now we know that they may have a little mass, but they are almost chiral, right? So in the rest frame of the pion, these muons are mostly 100% polarized because the neutrinos have an handedness, and this reaction do not occur in nature. So now, if you consider not the spin, but the magnetic moment of the particle, which is the gyromagnetic ratio times the spin, So you have the magnetic moment, which would be always anti-aligned with the velocity vector in the pion rest frame. So this is what we call audacity, because that was introduced by Roger, because it's different from spin polarization, because there is a charge in the magnetic moment. So for the negative muons, the magnetic moment reverse sign. And the takeaway message is that in the pion rest frame, this magnetic moment polarization is almost 100%. And now if you look at what you have on the ground, because of course that was in the pion rest frame, so you need to apply a Lorentz transformation to calculate polarization of the muon flux, for example, at sea level. You see that this would be depend on the energy, but without entering too much into the details, you can have up to 50% polarization. And the thing is interesting is that so this muon will of course decelerate and sometimes be captured also by atoms before they decay, or molecules. And even when they're captured, they actually can still retain some of their polarization. For example, when they're captured by a carbon atom, they retain still 50% of their spin or magnetic moment polarization. So the muons are on average magnetically polarized. So now let's make the connection with biophysics. So there is also something that is actually Parity, and you may know this, but ours is made of right-handed sugars. So they are right-handed by human convention. You have here the unit monomer nucleotide of DNA. So you have, or RNA, so you have basically the phosphate group, a sugar, which is chiral, meaning that it has a configuration. It can come in two configurations that are mirror images of one another. But for some reason, RNA and DNA are only using right-handed sugars, so ribose or deoxyribose. And then you have the bases, of course, that are coding for the genetic information. So, and these units are repeated along the helix. And the fact that the sugars are actually right-handed, it allows stability for the molecule, and it will make a right-handed helical structure. So we are not actually using this. And the question is why? Why we are only using white type of sugars in DNA and RNA? And RNA and DNA code for amino acids, which are the building block of proteins. And these are the building blocks of life, the nucleic acids and the amino acid, and there were experiments that were trying to mimic actually the prebiotic earth to see if it's possible to produce amino acid in such environments. And you can see here the result of this very famous experiment. So they actually managed to get amino acid, but the thing is that when you produce them by laboratory experiment, you always get equal quantities of both right-handed and left-handed molecules, while life choose only to use one type, one enantiomer, one mirror image over the other. So there is also another interesting puzzle, is that there is an asymmetry in left-handed amino acid over right-handed that is found in meteorites, but only a particular type of meteorite, the carbonaceous chondrites. And you can see some of them are displayed here with their enantiomeric excesses. So the definition here is just the number of right-handed molecule minus left-handed molecule over the total. And sometimes it can show a symmetry of 20%. But well, there were some debates. So because meteorites, of course, fall on Earth and then they are found, it may have some bias due to Earth contamination. So what we are looking for now is if there are any enantiomeric excesses in situ when we actually bring back samples to Earth. So you may have heard of Hayabusa 2, which is a mission, Japanese mission of JAXA that came back December 6 last year with samples of asteroid Ryugu. And there is another mission coming in 2023, another one from another asteroid, Bennu, and one of their goals is to analyze if there are any excesses in amino acids or the chiral organic compounds that they would find in the samples. So now I will say a bit of history. So how this homochirality in the living organism was discovered. So in 1769, Chiral was examining tartaric acid. So really everything started with wine here. This is from wine fermentation, so on corks typically. And this substance had a property that was not really understood at that time, that is optical activities. And that was studied by Jean-Baptiste Biot. So they were taking natural substances and putting them into solution, and they were seeing that actually the substances were able to turn the plane of polarization of linearly polarized light to the left or to the right. So they were calling them levorotatory or dextrorotatory. And they were thinking, okay, this must have some molecular basis. And then Pasteur actually took a racemic mixture of the same tartaric acid, but one made in laboratory. And it was human-made. I mean, it has the two actually. The two mirror images. So this is a drawing by Pasteur himself. And what he did is that he separated them. So he was the first one to do the separation of the racemic mixture. So with a tweezer, he separated the crystals that were mirror image and from the other mirror image. And he went to Jean-Baptiste Biot and he showed to him that one type was rotating the plane of polarized light to the left and the other one to the right. So that was Jean-Baptiste Biot really said to him that this experiment touched his very heart because he was loving physics so much. So Pasteur also saw that the tartaric acid, the one that comes from natural compound, because it was found in wine, right? So this tartaric acid only had one type of crystals. And he said that he was trying to understand why in natural substances, in living organisms, there is only one type of mirror image. And he said it must be due to the existence of some disymmetric force. And this was in 1848, so it was a century before the discovery of the parity violation in the weak interaction. So after, of course, it was discovered, people tried to make the connection. This is what the point I wanted to make, because so they were trying to make this what was anticipated by Pasteur, to try to understand if the weak interaction could have caused homochirality in living substances. So there were many possible routes that were explored. So I make this table. I will have them. So I will go briefly into these different scenarios. So you have, first you see that it's divided between prebiotic and biological. So the prebiotic scenario is that you say that the homochirality of the building blocks themselves, the simple molecules that form the biopolymers, so either amino acids or sugar, you can make optically pure soup, meaning that you will have 100% of one type of mirror image. And then from this prebiotic soup, you are able to produce biopolymers. So you want to produce an asymmetry, let's say in amino acid. So when after the discovery of the parity violation in the weak interaction, Abdus Salam and others try to calculate what would be the energy difference induced by this weak neutral currents in amino acid. So they just added this term to the Hamiltonian and they calculated the difference in the energy level induced by this PVED. So they reported 10 to the minus 17, which is quite small. But then I said, okay, maybe there is some phase transition and there is a lot of research ongoing about this that is actually able to make it homochiral. Then if you irradiate now samples of amino acid of a racemic mixture, 50% of each with ultraviolet circularly polarized light, that lead to differential destruction of one enantiomer over the other. And this has actually be proven to work and in laboratory experiments like the synchrotron Soleil at Orsay. It doesn't necessarily involve the weak interaction, but it must involve a source of ultraviolet circularly polarized light that would have irradiated the molecular cloud. And it depends on the photon energy. So also if you take, for example, energy of 6.2 electron volt and 10.2 electron volt as these experiments took, then the sign of the enantiomeric excess would reverse. So that's also a constraint for the astrophysical model. I put amino acid next to radioactive substances, so lead to differential destruction, but the electrons will lose their spin polarization very fast because they scatter. And I mean, it has not been really convincing. So there is a debate on this. I mean, the level were always something like 0.1% at best. Then you have an enantioselective chemistry using low energy spin polarized electrons, and this works as well. But it doesn't necessarily involve also the weak interaction. You must produce somehow in your environment when life started, low energy spin polarized electron. So that's for the prebiotic. So you can see that it's promising that some experiments show that it's actually can produce enantiomeric excess at level of few percent. This is still lower than what is found in meteorites, and we need to think about an amplification mechanism just to actually explain what is seen in the meteorites, but also to amplify it to make it homochiral before life started. And then you have the other types of models. If life started actually with the two possible helicities, because it's actually possible to polymerize and to have like chiral domains of left-handed helices and right-handed helices. And then something happened because we don't know what is the transition from how the transition from inert to living happened, right? But when it started to self-replicate, then what you can do is that you can induce bias into the evolution. So they will just one of them will evolve more rapidly than the other. So it's the same as actually mutations that occur, but the thing is that the question we ask is how life would react to polarized radiation. If it's ultraviolet circularly polarized light or high energy polarized muons that naturally occur all the time because we are irradiated all the time by muons. And so it has not been reported yet. We are thinking about experiments to actually probe if there is any biological response of, let's say, bacteria, for example, to circularly polarized or spin polarized radiation. But there is one effect also that was discovered more than a decade ago, which is called the chiral-induced spin selectivity effect, that actually showed that helical molecule can filter one type of spin polarization of low energy electrons. And this is actually quite high. And this effect, has been observed by many different groups, and there are theories that try to explain it using the spin-orbit coupling of molecules. But the thing is that the magnitude of the effect is still not really clearly understood. So it may be that helical structure actually which are naturally formed when the biopolymer are formed from polarization, then they are starting to self-replicate, and then you could induce a small bias, which would lead to homochirality. Okay, I think I spent too much time on this slide. So this is the connection now between the three items. And what we did with Roger is that we tried to calculate this small bias that may have been induced by cosmic rays, by spin polarized cosmic ray on the biological molecules. So we are not biologists. And as I said, the mutation level due to muons are poorly documented. I mean, I haven't seen any experiment calculating the mutation cross-section to muons. This is ongoing research. I think people also start to do this, irradiate biological samples with muons. But what we did is that we consider a very simple Barber pole model for the electrostatic potential. So we take one molecule of DNA with a Barber pole electrostatic potential and its mirror image. And so what we have to do is that we have to couple this molecular chirality, which involves the magnetic moment, and which is this magnetic moment polarization of the cosmic ray. So this we have a non-perturbed trajectory, and of course, then it would be exactly the same effect for the two molecules. But then if you have magnetic polarization, you have this term that appear in the force, and you see that this is like a Stern-Gerlach effect. This is the magnetic moment, and this is the magnetic field that the cosmic ray see from the molecules. So not to enter into the detail, what we did is that we calculated the difference in the ionization rate, taking ionization as a proxy for mutation between the two molecules. And we did a classical calculation, which is, of course, a strong approximation, because it needs, of course, to be treated quantum mechanically. But it was more like to see what level it would be. And the difference in ionization, it's something like I reported in the table between 10 to the minus 6 to 10 to the minus 8. So it's still very small. But of course, it beats 10 to the minus 17. So the question is, can this be large enough? Because the thing is that maybe even if it's small, we are irradiated all the time by cosmic rays. Maybe the flux of cosmic rays was higher in the past. So there are a lot of maybes here. But the thing is that now we would like to see if there is, as I said, a response to polarized radiation, and to perform a calculation that would be actually more complete, because maybe we underestimated some effect. So there is a difference, and so that's the summary. So we propose that polarized cosmic ray muons act as a chiral evolutionary pressure, and that the homochirality will emerge on an evolutionary timescale. The question is, what is this timescale? Because of course, if it's a billion years, then it's obviously not a good model. This is a testable idea, and it would of course depend on the environment, because on Earth at ground level, we are dominated by muons, but in other environment, as I showed before, it may not work that well. So we were thinking about Mars, because there were some questions about hot springs that were actually spotted by Spirit in 2008. And so that's from a paper by David Dimmer. So in his model, this structure, the polymerization of long chain of simple molecules, can arise in hot spring because you have wet dry cycles conditions. And then if you manage to form simple biopolymer, that is a first step, right? Because then something that we don't know must have happened to make them self-replicate. But that's a first step. You can form chains of long biopolymers up to 100, I think, in laboratory. And then they showed that in natural hot springs, this could happen as well. And the interesting thing is that, as I said, spirits spotted something like resemble this same environments that where we found the earliest sign of microbial form on Earth. So the question is, could Mars have also be able to have the conditions that could have led to life, but because of Mars evolution, then either life is still there but underground, or it didn't have time to really form. So there was also another important point is that in 2018, they discovered a lake 1.5 kilometers beneath the surface. So we were just wondering where the muon would be dominating. So actually we did the calculation at different environments. So this is Earth again. So you see that the muons, they dominate, really start to dominate at ground level, and then they would decay underground. But on Mars, because the atmosphere is thinner, then they will start to dominate something like 10 meter water equivalent below the surface. And meantime, so I could, well, if there are questions, I could show you what happened for other environment. But as I said, for example, for Venus, this muon component would dominate something like 40 kilometers above the surface, which is what I said, where there is actually the, when people think it's the habitable zone of Venus. So just, it would be very interesting if we could really start to make experiments and to see how muons really interact with biological molecules. So I will summarize my talk. So the origin of homochirality is a fundamental problem. It connects biology, chemistry, and physics. The question is, does it happen by chance that the particular handedness within the living organism, or is it deterministic? In that case, it would be connected somehow to the weak interaction, and we need to understand the connection. Does it happen at the prebiotic or biotic stage, and in which environment? Are cosmic rays responsible? So we were studying if it's muons or electrons, but the electrons lose their spin polarization very fast because they are scattering. So while muons can retain their polarization even when they are captured by the molecules. Is it due to the magnetic moment polarization or the spin polarization? If it's due to the spin polarization, then I haven't said that, but you have more positive muons than negative muons, but the charge ratio is quite, it's not that high, it's 1.2 to 1.4. While if it's linked to the magnetic moment, which we showed in our calculation, this is due to this second term, mu dot b, then for positive and negative muon, it has the same sign. What is the homochiralization timescale for this model? Is the conflict necessary? Because if you introduce a conflict between also the different, the two mirror image life form, then you will speed up the homochiralization timescale. This has been shown also because if you, for example, you want to, antibiotics are based on the right-handed molecules. If you want to stop the growth of bacteria, you can introduce the wrong-handed amino acid in the bacterial environment. So So if one would produce the food and then introduce the wrong-handed molecule in the environment of the mirror image life, then of course you will have a conflict and you will speed up the homochiralization timescale if you are able to do a very small bias in one of them. These are just the pre-predictor equation. So it's a testable idea. There will be sample returns that could actually tell us more about if there is any enantiomeric excesses from surface of subsurfaces. So I talk about the asteroids. There was also the Rosetta mission. That one of the goals was to actually see if there was an enantiomeric excess in the organic compounds of the comet, but as you may recall, the lander bounced and found itself in the dark, so this particular experiment did not work. And we are also, I think, I don't know when in the future, but thinking of digging 2 meters below the Martian surface to actually also probe the chirality of the organic compound found there. So we could test the idea with experiments if we irradiate biological samples with polarized beams to see if there is what is really the size of the effect. And we can look for chiral molecules at different astrophysical environments. And I think this was propylene oxide was the first one in 2016 that was actually detected in the interstellar medium. So, okay, I will stop here. Thank you very much. And I'm happy to take questions.
Thank you so much, Noemi. Thank you very much. I guess we have quite a few questions. This was somehow a very fundamental, sort of stunning idea with the ludicity. I hadn't realized that myself at all. Maybe that's right. I've seen one question. Well, Skylar, I think was the first.
Yeah, hi. Thanks for a really thought-provoking talk. So I have a kind of naive question and a kind of picky technical comment. I'll start with a question. If we think of something like spontaneous symmetry breaking, which is kind of familiar in the context of particle physics, does that not also work at a biological level? So when you have left and right-handed sugars, for example, that are metabolized differently in all of the life forms that we see on Earth, couldn't it just have started with one as opposed to the other? And because the metabolic pathway only worked on the first one to show up, that's it. There's nothing fundamental here, but it just kind of followed the first path it was given. And the picky comment is that, of course, I'm sure you're aware of this, but for generating the baryon antibaryon asymmetry, the parity violation and the weak interaction doesn't really get you there. What is needed is CP violation, which doesn't come from the weak interaction. And so I think it might be a little bit misleading to trace parity violation, which may be connected to life, as you described, to the fundamental CP violation, which is required to give us baryogenesis. But thanks, that was, as I said, very thought-provoking.
Sure, the slide was just to show that the pion decay is mediated by the weak interaction. So this is what caused the muons to be polarized. And the slide on the, I can show it again, but it was a historical slide to show when this effect has been discovered and that it's a very tiny effect that could have large consequences. So of course, the pion decay, it doesn't violate the P, but it violates the P, right? So it's a violation of parity anyway. And this is why the muons are all magnetically polarized on average. If you didn't have this parity violation in the weak decay, then they wouldn't be magnetically polarized on average. So this was just to show the connection between the weak interaction and this polarization in the cosmic shower. Then if we now start the first comment, we don't really know and why the metabolism would have preferred right-handedness naturally over left-handedness. that, you know, I mean, it's also as speculative as the rest, but if there is no really preference, these experiments that are made by our colleague David Dimmer show that you can actually polymerize the two types of helices in the environment, and that the size of the, you know, how long are they, it would depend on the environment and many factors, right? So you could also say maybe the longest one started over, you know, but then you always need some kind of bias. So it's like the chicken and the egg problem, right? If you want an asymmetry in the building blocks, and then even if it happened by chance and it started to be, you know, a bit more than the other, the question is if life also reacts to polarized radiation. It's an interesting question per se. So this is why, I mean, whatever we learn from the experiment, it would be interesting on many fronts. I don't know if Roger joined the call actually, and he wants to comment on this, but
He did.
Yes, Georgia is there, I think.
ah, he's there. Okay.
Yeah.
Yeah, I'm here. Half asleep, but I'm here.
Well, thanks.
I guess my answer is the same as Noemi's. Firstly, I completely agree that there are what are called 3 Sakharov conditions in the early universe, which are, you know, and one of them is CP violation, and parity, you know, charge parity. Another is baryon number, and then the third is getting out of equilibrium. And
Exactly.
our point was a much more modest one, that very small asymmetry, which no one quite understands, can lead to one species of baryons, not the other. That's a sort of, it's just an analog. So completely agree that parity violation alone does not do this in the early universe. The other point Noemi said was that, you know, in our view, it could easily have just been spontaneous symmetry breaking. You break to the left or you break to the right, and, you know, it's just a pure matter of happenstance. That to us seems a perfectly reasonable thing to guess, but the alternative also seems reasonable. And I think the thing that we're most excited about is it might be possible to distinguish this. And one way you might do this, for example, suppose you found a whole bunch of essentially isolated extremophiles on the Earth, and they've developed their own societies with the opposite chirality, then I think we'd have a hard time making our case that it was, you know, cosmic rays were making it into a causal process.
Right. Thanks, Roger. I guess Christian had a question.
I had a question here. Thanks. This goes more in the astronomical context, and so I think that amino acids have also been found in molecular clouds. Maybe that's not correct, but I think it's true. So would your process also work in molecular clouds? I mean, this is also gas. You could have showers of muons, and they could change these amino acids in the molecular cloud. So this is a prebiotic process then, and all matter that forms planets and atmospheres and life will be formed by these molecular clouds that have been already threatened by this muons. Is that something reasonable, or?
The thing is that do we know the density of these amino acids? Because it seems okay. So people look at this model with the molecular clouds in the context of UV circularly polarized light, right? Because they saw that they can produce an enantiomeric excess of 2 to 3% by irradiating, you know, the racemic mixture with 100% circularly polarized light. And the thing is that first, okay, you have to come up with a source of circularly polarized light in astrophysics, but that's, let's say there was one, but even if there was one, then you would get excesses at the level of few percent, right? So if it's prebiotic, then you still would need an amplification mechanism, which is maybe hard to think about in these clouds. And for cosmic rays, it would be, I think, even, it could be even less. It would depend on the flux of cosmic rays, of course. But
will it also depend
on
on
the density and the cross section that you have? So I don't really know what is the density of amino acid, but then I would not expect it to be to be very high. So then, of course, if you form few percent excesses and then you have collapse and etc.
Does it also depend on
need to
the?
think about the step 2, so the amplification process.
So how much does it depend on the gas density? I mean, the Earth atmosphere is of course much denser than the molecular cloud, and I assume that the muon flux is also depends on that, the gas density, you know, on because you have to.
So this is what I think I showed in this.
Yeah.
Come back to the slide where I was comparing the different environments. This one. Okay, this is for different atmospheres.
Okay, yeah, I
not
see.
for a molecular cloud, but the thing is that you see that it's already quite different.
Yeah, that is completely different. Okay.
And this is the density of the
Okay.
different and the altitude. So you can see it's really function of grammage.
Okay.
Where the muons would dominate.
Okay, thank you.
Okay, Andreas Trautner had a question.
Yeah, this is just a follow-up to this nice question about the amino acids. So I'm wondering, is like, what is the, say, redshift when these amino acids or these molecular clouds first form? Because I mean, they may have a lot of time, say, to be around and get polarized. No?
You mean by cosmic rays?
By whatever mechanism. I'm just the question is like, how long have these? How long? What is the first, say, redshift, or what is the first time in the evolution of the universe when these molecular clouds first arise?
Well, I think the good question is how long it takes to form this amino acid, but that's I don't know. I mean, it's not my field. What I think about the source is that for the circularly polarized, it was the early sun, and there was a double scattering. So first scattering produced linear polarized light and second circularly polarized. And at the level of something like 20 or 30%, because this is what is seen is in infrared in Orion. So they think that in UV it could have been the same, which is discutable. But then this is the level of polarization. It was at the very early when the sun was in Titori phase. So this is what you know.
Yeah.
The other type of models, but I don't know precisely how much it would have irradiated the amino acid in the molecular clouds.
Okay, Roger wants to come back on something. Roger?
Yeah, hi. Hi.
Hi.
Just I didn't hear all of the talk, Noemi may have said this, but there was a recent detection of propylene oxide in interstellar gas, and that is a chiral molecule. There was no detection of a chiral preference in the spectra, but I guess I don't, the question is, there may be people in the audience who know how difficult it would be with a molecule like that was chiral, then to use the circular polarization or whatever to see if there really was a chiral preference in interstellar space. Is that completely out of the question or not?
Can anybody answer the question? It's a pity Paola Caselli is not around. She will look at this later in the recording. Maybe then she can email back to Roger an answer if nobody else can answer.
Yes, and I can even add another question, not even in the molecular clouds, but maybe, you know, like atmospheres, like Venus, and if we can, because there was this phosphine, right, debate. So
yeah, but just
chiral molecules in situ also.
Naomi, you know, the muon survival time would have to be long enough for this to work, right? For your mechanism to work. That's why you were saying the densities had to be high.
Yes, but you can see here for Venus, it's interesting that it's.
No, I meant in any interstellar medium.
Yes, an interstellar medium, of course. It has to have equivalent grammage, I would say. So you
Yeah.
have the peak of muons, and it will happen exactly at this, you know, I mean, it's a range of distances from the accelerator, which is a shock, let's say. So you have a shock, it accelerates cosmic rays, and then of course they will, if you have a PP interaction, then you can form muons, but they will not traverse all the molecular.
No, that's right. I guess that's the calculation that needs to be done there. Probably not possible in real time now. Okay, Roger, do you have another point? Your hand's still raised. I guess not.
No.
Okay. Hi, Roger. Well, you know what we normally do is we have an open-ended Zoom session. So all those who want to sort of continue informally discussing afterwards are very welcome to do so. Maybe we let Noemi also get a cup of coffee as well or something. But before I end the formal conclusion symposium, I just want to put up an advert for next week. So I'll just take the screen just for a moment, if I may. So next week, we're going to take a detour from our solar system, very short hop to the center of the galaxy. We're going to hear about some of the theoretical work that's been done here in Heidelberg on understanding dynamics and processes in the interstellar medium in the central region. So with that, I think I'd like to ask everybody to open their microphones and videos, and let's give Noemi a really good send-off for such a thought-provoking and interesting talk. Maybe we'll be talking about this, or our ancestors will, in 100 years' time. Thanks very much, Noemi.